On the test bench is a single low-power memory package pulled from a qualification batch, lot numbered, dated within the last 18 months, and attributed in the test log to Changxin Memory Technologies, the Chinese DRAM producer that most Western analysts had categorized as years away from this tier until the yield data began contradicting that assessment. The package looks, from the outside, like any other component destined for a flagship smartphone. The layers underneath do not support that surface reading. We will move through this object from the exterior marking inward to the die itself, reading what each layer exposes about the process that produced it, and the pressure that shaped that process, and the deepest layer carries a fact the restriction memo did not model. The package on this bench is stamped with the designation LPDDR5X. That designation belongs to JEDEC, the global standards body that defines the electrical and physical specifications a memory module must meet before it can legally carry that name. JEDEC sets the speed grades, the voltage rails, the power down states, and the thermal envelope. A producer that prints LPDDR5X on a package is making a testable assertion that the module inside meets those parameters. Changxin Memory Technologies claims a rated transfer speed of 10,667 megabits per second for this product, which places it at the top of the LPDDR5X specification window. No independent benchmark of a shipping Changxin LPDDR5X unit inside a consumer device has been publicly confirmed as of the time this analysis was prepared. The rated figure is the company's own claim, and the gap between a rated specification and a confirmed, independently measured result in production hardware is a gap this dissection will return to. The lot number stamped on this package exists because qualification requires traceability. Without it, the test engineer who evaluates the module cannot tie a pass or fail back to a specific production run. The marking is not branding. It is the minimum paperwork the socket demands before the package is opened. Beneath the exterior label is the package substrate, the laminate layer that routes electrical signals between the memory die and the circuit board of the device that will carry it. Substrate materials at this tier include dielectric layers, bonding compounds, and the conductive traces that form the signal paths. A full independent materials analysis of a Changxin LPDDR5X substrate has not been publicly released as of this writing, so what follows is drawn from tear-down adjacent reporting on Changxin's broader memory product line rather than confirmed analysis of this specific package. What that reporting suggests is that the substrate supply chain for Changxin's products is substantially domestic, a shift that accelerated after 2019 when entity list placements complicated the supplier relationship several upstream materials vendors had maintained with Chinese memory producers. When a foreign supplier for a bonding compound or a specific dielectric formulation becomes legally difficult to work with, the producer does not halt production. It qualifies a domestic alternative. That alternative leaves a material signature in the substrate. The substrate is not where the performance story of this package lives, but it is where the first wave of supply chain adaptation becomes physically embedded. The cost of that adaptation is paid not in speed or power, but in the engineering time required to validate a replacement material to the same process tolerance as the original. The next layer down is the interconnect, specifically the array of solder bumps that bridges the substrate and the die. Bump pitch, the center-to-center spacing of those connections, is a proxy for the precision the producer can maintain across volume production. A tighter pitch means more signal paths in the same footprint, which matters at speeds like the one this package claims. Changxin has not published bump pitch specifications for this product publicly. What the rated speed figure implies, however, is significant on its own terms. 10,667 megabits per second is achievable only if the electrical path between die and substrate meets the signal integrity demands of that speed grade. A producer that cannot hold the interconnect geometry within tolerance will fail qualification testing at that speed. The qualification pass, if confirmed by production use, is therefore indirect evidence that the interconnect layer is performing within the required window. This is inferential. A qualification pass implies a functioning interconnect, not the reverse. But it is the type of inference a test engineer draws when reading the same record. The interconnect layer exists because the die cannot communicate with the board directly. It is the translation layer, and its geometric precision is determined by the packaging equipment the producer has access to. A producer denied access to the most advanced packaging tools must achieve the same signal integrity outcome through process tuning and design margin. The layer does not announce this adaptation. It simply performs or fails. The die surface is where the equipment restriction calculates its exact cost in silicon. Changxin describes its LPDDR5X as built on a 16 nanometer class process node. In DRAM manufacturing, node naming conventions do not translate directly from logic chip nomenclature. DRAM nodes refer to the half pitch of the memory cell array, and different producers measure and name them with enough variation that cross-producer comparisons require care. 16 nanometer class in DRAM places Changxin behind the leading-edge producers. SK Hynix, Samsung, and Micron are working on processes described in analyst and company disclosures as sub-15 nanometer or better for their current leading products. That gap is real and measurable in cell density per unit area. A producer with access to extreme ultraviolet lithography at scale would not choose a 16 nanometer class process for a product where a tighter node would improve density and lower cost per bit. The node is not a preference, it is a ceiling, and the ceiling is set by what lithography equipment has been legally deliverable to this producer. The die surface is where the policy document that restricted that equipment becomes a geometric fact expressed in silicon. The cell pitch on this die is the restriction's most precise signature, and it is the layer the teardown identifies first when it opens the package. The analogy that makes the node gap concrete without flattening it: a 16 nanometer class cell in DRAM is roughly twice the width of the cells in the most advanced leading-edge DRAM being manufactured elsewhere. The difference in width between what Changxin builds and what the leading-edge producers build is approximately the difference between a thread in a cotton fabric and a thread in a silk one. Both hold the weave together. Both produce a functional garment. The person wearing the garment cannot feel the difference in use. What the difference does determine is how many cells fit on a die of fixed area, which is how cost per bit is set. The phone user does not feel the node gap. The cost accountant does, and as the leading edge producers move further below 15 nanometers, that cost gap widens. Moving into the cell array interior, the scale argument resolves. Changxin is reported by industry analysts tracking wafer capacity, not by independently audited figures, because the company does not publish line-level output data, to be running on the order of 300,000 DRAM wafer starts per month. To make that quantity physical, the wafers from a single month of output at that rate, each a 30-centimeter disk of silicon carrying hundreds of individual memory dies, would cover a surface area larger than 4 full-size basketball courts laid flat. Analyst estimates place Changxin as approximately the world's 4th largest DRAM producer by volume at this output level. Its global DRAM market share is estimated to have moved from roughly 4% to roughly 8% within a single year. These are analyst estimates. They carry the uncertainties that apply to any capacity figure derived from inference rather than audited data. The inference that follows from scale, however, has its own weight. A producer running 300,000 wafer starts per month has either solved the yield problem or is sustaining a financially visible loss at a scale that analyst tracking would detect. The cell array at this volume is not a demonstration. Its existence at this output rate is the argument. The power architecture layer confirms the target socket. LPDDR5X is not a marketing tier within the LPDDR family. It is a JEDEC-defined electrical specification covering the voltage rails, power down modes, and thermal envelope appropriate to a battery-constrained mobile device. A die that meets the LPDDR5X power specification is, by definition, built for the mobile socket, the smartphone, the thin laptop, the tablet. Changxin's LPDDR5X is the exact memory class a flagship phone requires. The decision to build LPDDR5X rather than server DRAM or graphics DRAM reflects where volume demand is concentrated and where the qualification pathways are shortest. The mobile memory segment is the highest volume DRAM category globally. A producer building scale needs to be in the segment where the sockets are most numerous. The power architecture is not an engineering choice made in isolation. It is the producer's answer to the question of where qualified volume can move fastest, and the answer was written into the die before the first wafer ran. The deepest layer is the qualification record, and it is where the restriction's internal logic becomes most legible. The die on this bench has been described in industry and sourcing coverage, not in publicly released original equipment manufacturer qualification documents, which have not been made public, as a technically qualified candidate for production use in mobile devices. The qualification pathway it entered was accelerated by the supply constraints that followed the tightening of DRAM-related export controls and the entity list placements that complicated relationships across parts of the memory supply chain. A supplier that enters qualification under supply pressure conditions and passes that qualification occupies a structurally different position than one that entered under normal competitive conditions. The test engineer who signs the qualification record is not making a geopolitical statement. The record itself is the statement. Once signed, the qualification does not contain a sunset clause tied to the emergency that prompted it. The original equipment manufacturer's incentive to maintain the qualification relationship does not expire when the supply pressure eases, because the alternative, removing a qualified supplier and replacing it, is its own qualification cost. The restriction created the scarcity. The scarcity created the qualification opportunity. The past qualification is now a supply chain fact that exists independently of the original restriction. This is the layer where the restriction's logic inverts. The policy instrument was designed to prevent this producer from reaching the qualification threshold by limiting its access to the equipment and materials needed to close the performance gap. The producer closed enough of the gap on the node it could build, with the equipment it could legally acquire, using the domestically qualified substrate materials it had substituted for restricted foreign inputs, to pass the test the socket requires. The restriction is visible in every upstream layer, in the node ceiling at 16 nanometers, in the localized substrate materials, in the interconnect precision achieved through process tuning rather than the most advanced packaging tools. The cumulative effect of navigating each of those constraints is the die now sitting in this qualification record as a pass. The deepest layer does not reveal a workaround that defeated the restriction. It reveals a product that the restriction itself shaped, adapted, and ultimately delivered to the qualification threshold. 3 things this dissection cannot settle, stated plainly. The qualification candidate status of this die rests on industry and sourcing coverage, not on publicly released original equipment manufacturer documentation. The gap between a claim specification and a confirmed independently measured result in a shipping consumer device remains open. That gap is real and the dissection cannot close it. Second, the analyst estimates placing Changxin at roughly the world's 4th largest DRAM producer and at approximately 8% global market share are not derived from audited production figures. The yield inference drawn from scale, the argument that 300,000 wafer starts implies exit from yield instability, is structurally sound but not confirmed by process data in the public record. Third, a 16 nanometer class process carries a cost per bit ceiling that tighter nodes do not share. As the leading edge producers move further below 15 nanometers, their density advantage grows, which translates to lower manufacturing cost per gigabyte at equivalent die size. Whether Changxin's current node position remains cost competitive as the leading edge extends that distance is a question this qualification batch cannot answer. What the dissection can settle is narrower. The die is real. The qualification pathway is real, the scale is real, and the restriction's structural imprint across every layer of this object is legible. Whether the object at this node, at this yield, at this cost structure, is durable across a full market cycle is the question a single test bench package does not contain. The package on this bench is not evidence that the restriction failed in any uncomplicated sense. It is evidence that the restriction was the dominant environmental pressure under which this object was formed, and the object adapted to that pressure with enough fidelity to reach the qualification threshold. Every layer opened in this dissection is a readable record of that adaptation. The localized substrate materials record the upstream supplier relationships that were legally complicated. The 16 nanometer class node records the lithography equipment ceiling that equipment controls imposed. The power architecture tuned to the mobile socket records the market entry calculation a producer makes when it needs to move qualified volume fast. The wafer output that implies solved yield records the consequence of sustained industrial investment under sustained constraint. The qualification record at the deepest layer records the moment the socket accepted the object the restriction shaped. The analysis shows that the restriction and the die are not opposites in this story. The restriction is the die's biography, written in process nodes and substrate materials and qualification timestamps. What the restriction built in the end was the exact pressure that forged the thing it was trying to prevent. The next object this channel opens is your call. Leave it in the comments. Which die, which system, which stack do you want on the bench next, and what do you think its deepest layer will say? If this dissection was useful, subscribe and turn on notifications so you are there when the next incision begins.